In this video, we will look at the binomial probability distribution. To determine whether a probability experiment is a binomial experiment, each observation is binary, meaning it has one of two possible outcomes. Some examples: accept or decline an offer from a bank for a credit card, have or do not have health insurance, vote yes or no in a referendum. A binomial experiment is a probability experiment that satisfies the following four requirements. There must be a fixed number of trials. Each trial can only have two disjoint outcomes or outcomes that can be reduced to two outcomes. These outcomes can be considered as either success or failure. The outcomes of each trial must be independent of each other, and the probability of success must remain the same for each trial. When we refer to a success, that doesn't necessarily mean that it's a good thing. It is simply the outcome that we are looking for. A binomial distribution gives the outcomes of a binomial experiment and the corresponding probabilities of these outcomes. We use the following notation. P of S is the probability of success, P of F, the probability of a failure, and we will use P and Q to represent the assigned values for the probability of success and failure respectively. N represents the number of trials, and X represents the number of successes in N trials. So X equals 0, 1, 2, all the way up to N. Determine if the following experiment satisfies the requirement of a binomial distribution. We're considering the experiment flipping a coin. So we will look at the four requirements and see if they are verified. Fixed number of trials. Although it's not specified, but yes, it would be specified in a further example. Two possible outcomes. Yes, heads or tails. Trials are independent. Yes. The probability of success remains constant. In this particular example, if we consider a success to be heads, the probability of heads would be 5. Compute probabilities of binomial experiments using the formula. For n independent trials, the probability of x successes equals this formula. It calculates the probability of x successes in n trials given a particular value of p. N represents the number of trials, x is the number of successes, n must always be greater than or equal to x, and x can equal 0, 1, 2, so all the way up to n. Using the formula of the binomial, find the probability of getting exactly 2 heads in 3 tosses of a coin if it's fair. N equals 3 because there are 3 tosses. X equals 2 because we want 2 heads. Probability of success, or P, is going to be 0.5. Now, because we are referring to getting heads, that will be our success. Because the probability of success is 0.5, the probability of failure is also 0.5 by the complement rule, or by considering the probability of getting tails. So the probability that x equals 2 is equal to 3c2 times 0.5 squared times 0.5 raised to the 3 minus 2 power. 3c2 is equal to 3. Using our calculator to evaluate, we get that the probability of getting exactly 2 heads is equal to 0.375. A survey found that 1 out of 5 Americans say he has visited the doctor in the last month. If 10 people are selected, find the probability that exactly 3 will have visited the doctor in the last month. So visited the doctor in the last month will be our success. We're surveying 10 people, that's our fixed number of trials. We want exactly 3 to have visited a doctor. So n equals 10, x equals 3, p is equal to the probability of success. 1 out of 5 Americans say he has visited the doctor in the last month. So our probability is 1 out of 5, or 0.2. So the probability of failure is 1 minus 0.2, or 0.8. The probability of getting exactly 3 who have visited the doctor in the last month, 10c3 times 0.2 cubed times 0.8 to the 10 minus 3. 10c3 is 120 times 0.2 cubed times 0.8 to the 7th power. Using our calculator to evaluate this, we find that the probability is equal to 0.201. A survey from a research company found that 30% of teens receive their spending money from part-time jobs. If 5 teenagers are selected at random, what is the probability that at least 1 will have a part-time job? Remember, the probability of at least 1 is equal to 1 minus the probability of none. When we refer to the probability of none, we're talking about none of the teenagers having a part-time job. If 30% of teens have a part-time job, then the probability that they do not is 0.70. So the probability that all 5 do not have a part-time job is 0.70 raised to the power of 5. Using our calculator, we get the probability is equal to 0.83193. Compute probabilities of binomial experiments using the table for the binomial. Table 3 on pages A3 to A6 in your textbook gives some of the binomial probabilities already calculated for you. The steps: you want to find the value of n, then find x for that n, find p across the top, and match it up to get the probability, p of x for n and p. Using the table for the binomial, find the probability of getting exactly 2 heads in 3 tosses if the coin is fair. So n is 3, x is 2, and we know that the probability of success is 0.5. So we will see how to use the table next. Here's a screenshot of part of the binomial distribution table that you have in your green folder or your green packet and in your textbook. The steps for using this: first we want to find our value of n. In this problem, n was 3. And then we want to find our value of x. X is 2. So this is the first row that we're going to look at. Then we need to consider our probability of success. Since the probability of success was 0.5, we're looking at this column. Where those two intersect gives the probability of exactly 2 heads out of 3 trials. And this matches what we found using the formula in a previous example. A study showed that there is approximately a 15% chance that a woman will develop breast cancer over an 80-year lifespan. In a sample of 20, find the following probabilities from the binomial table. There are exactly 5 people in the sample who will get breast cancer. Since we're referring to those who will get breast cancer, we're going to mark that as our success. So from the problem, we know that a woman has a 15% chance of developing breast cancer. So P is equal to 0.15. We have a sample of 20, so n equals 20. In part A, x equals 5. So using the binomial probability table, we will find the probability that x equals 5. So here's a screenshot for the binomial table for n equals 20. First, identify n. We want x to be 5. So here's our row. And then we want to look at the probability of success, which we noted was 0.15. Where those two intersect, we'll give that probability 0.1028. Find the probability that there are at most 3 people in the sample who will get breast cancer. At most 3 means 3 or less. So we want the probability that 0, 1, 2, or 3 people will have breast cancer. So we're going to find the probability that x equals 1 plus the probability that x equals 2, 0, 1, probability that x equals 2, plus the probability that x equals 3. Using our probability distribution, or the table, we find that the probability of 0 is 0.0388 plus the probability that x equals 1. Sorry about the barking. The probability that x equals 1 is 0.1368. The probability that x equals 2 is 0.2293. Plus the probability that x equals 3 is 0.2428. So the probability that at most 3 people will get breast cancer is equal to 0.6477. Find the probability that there are more than 3 people in the sample who will get breast cancer. So our event is defined as more than 3. So the complement of this would be 3 or less. Applying the complement rule, we know that the probability of our event is equal to 1 minus the probability of its complement. In the previous example, we found the probability of 3 or less as 0.6477. So the probability that more than 3 people will get breast cancer is equal to 0.3523. Find the probability that there was at least one person in the sample who got breast cancer. The probability of at least one equals 1 minus the probability of none. Or that we have 0 successes or 0 women having breast cancer. Using the binomial probability table, we find that the probability that x equals 0 is 0.0388. So the probability that at least one person will get breast cancer is 0.9612. Compute the mean, variance, and standard deviation of a binomial random variable. The binomial probability distribution for n trials with probability p of success on each trial has a mean and standard deviation given by the following. You are taking a 10-question multiple choice test, and there are 4 possible answers for each question. You are interested in getting the answer correct. Find the mean, variance, and standard deviation. For all of these formulas, we need to identify the value of n, p, and q. N is the number of trials. There's 10 questions, so 10 trials. P is the probability of success. If each question has 4 possible answers, the probability you get it right is 1 over 4, or 0.25. The probability you get it wrong then is 3 over 4, or 0.75. The mean is n times p. Or 2.5. The variance is n times p times q, which equals 1.875. And the standard deviation is the square root of that. Which equals 1.369. A study showed that there is approximately a 15% chance that women will develop breast cancer over an 80-year lifespan. If 100 women are looked at, find the mean, variance, and standard deviation, then interpret the mean. N is 100. P is the probability of success, or the probability that a woman gets breast cancer, which is 0.15. Q is going to be 1 minus 0.15, or 0.85. The mean is N times P. Which equals 15. If I were to interpret this, this says that 15 out of the 100 women, or on average, 15 out of 100 women will get breast cancer over an 80-year lifespan. Our variance is N times P times Q. Which equals 12.75, and our standard deviation is the square root of that. Or 3.571. Now you will also need to read graphing a binomial probability distribution, and note that the only difference would be that you have to find the probability for each possible x given either n, either using the formula or the table, and then graph it just like we did in section 6.1. And we are not covering 6.3 or 6.4 of the textbook.